Good morning, students. Today let's discuss the two important topics, namely equipotential surfaces and electric dipole. Okay, means electric dipole moment and electric field due to electric dipole, and also electric potential due to electric dipole and the relation in between them, as well as axial and equatorial lines. Electric field due to axial line and also equatorial line. Both of them, and also on any arbitrary point P. All these things we will discuss in this present lecture. Right, let's start with equipotential surfaces. Right, the name itself says equipotential, means the points which are having equal potential, which is called as equipotential surfaces. Right, let me consider a charge plus Q. Plus means a positive charge Q. As this is a spherical charge, we will observe the concentric spheres. We will observe the means nothing but concentric spherical electrical field around that one. Right, we are observing that one. And now, always the electric field lines which are emerging out from this will be perpendicular to these concentric spheres, right? If you observe these things carefully, all these electric field lines are perpendicular to all these concentric spheres. Here we have mentioned two concentric spheres, or we can say surfaces. These two are equipotential surfaces. That doesn't mean these two has equal potential. No. Whatever the point you choose on any of the surface, means for example I am considering a point here and also a point here. Okay, this is point P1, this is point P2, and this is a point P3 and point P4. It means potential at point P1 is equals to potential at point P2 is equals to potential at point P3 equals potential at point P4, and so on up to infinity. Means infinite points we can mention on this spherical surface. Okay, those all points will have equal potential. Why? Because here if you observe carefully from the charge, the distance between the central charge and also to the surface is same. Means everything is radially outwards. Each and everything has the same distance. The same distance you are able to observe here. That's why as the distance is same and the charge is same, potential is also same, right? That is the reason V1, Vp1, Vp2, Vp3, Vp4 and so on up to infinity, which are the points located on this surface, will be equal. That's why we call the points which are lying on the particular surface having same potential will be called as equipotential surface. And this is also an equipotential surface, okay, but with another radius. This is another concentric sphere. Don't think this one and this one have same potential. No, these two have different potentials, but the points which are lying on the potential surface will have equal potential. It means, for example, again here you can consider here P dash, P1 dash, P2 dash, and here another point P3 dash, arbitrarily we can take. It means Vp1 dash is equals to Vp2 dash equals Vp3 dash, and so on, like that we can mention. This is for inside concentric sphere, and this is outside concentric sphere, right? This is nothing but called equipotential surfaces. Equipotential surfaces can be found not only around the spherical charge, we can see around a planar charge also. As we are dealing with equipotential surfaces which are two-dimensional in nature, right? That's why we cannot take a line charge here. But I can take here a planar charge. It means, for example, let me consider a plane like this now. which is a positively charged body, positively charged plate, it will exhibit electric field in this manner, right? This one will exhibit electric field like this in the both directions, that side and this side, right? If you consider here another two planes in this form, another one, these two are nothing but equipotential surfaces. This is one equipotential surface and this is another equipotential surface. Here if you consider Vp, okay, is constant here, means everywhere at this point potential will be Vp, at this point potential will be Vp, at this point potential will be Vp, at this point potential will be Vp only. Everywhere on this surface, if you check the potential, it will be same. And one particular thing that we have to remember here is this surface that we are taking should be parallel to the initial plate or initial source surface. Okay, it means see this one, this plate and whatever the surface that we have taken here should be parallel to each other. If this is not parallel, if it is inclined, we cannot see equipotential points, okay, because as the distance keeps on changing, means for example if you keep this is one plane, if you consider this is a plane which is having positive charge and it is exhibiting all electric field lines in this direction, straight electric field lines, and if you consider another plane exactly parallel to this one, okay, then only we can say in this particular plane each and every point will have same potential. For example, if I have tilted this plane, means I'm assuming in this manner, it means if you see the distance between here to here is very less, but from down to here is comparatively big, right? Okay, and this is a minimum distance, here it is a maximum distance. That's why potential changes, right? In this situation, whatever the point you take, it will not be same. Okay, it will not be same, means nothing but potentials are not same if you consider in an inclined manner. If you consider exactly parallel, then the potentials are same. That's it. This is nothing but called equipotential surfaces. Let's go on with electric dipole, right? Let's start that. Right, people better note down these things. These two will have some potential difference. Depending on this distance, those two will have some potential difference. And now these two also should be parallel to each other. Then only we can say these two will have exactly one constant potential difference. If they are not parallel to each other, that's all. Again, this is not at all an equipotential surface. If this is parallel to this and if this one is not parallel to this, then we cannot consider this as an equipotential surface at all. Okay, all right, that's it. Electric dipole. See, what is mean by, first of all, a dipole? Dipole means having two different opposite poles, which is nothing but called as dipole. For example, our earth has two poles, one is north pole and one is south pole. They both are exactly opposite towards each other. Okay, it means nothing but a pair of poles, and as they are two, that's why we call it as a dipole. Electric dipole is simply consists of one negative charge and also one positive charge which are separated a small distance d, which are separated by a small distance d. This pair or this system of charges is nothing but called as electric dipole, right? Now from here to here, if you see, this is nothing but called p bar, means nothing but this is electric dipole moment. We call this term as electric dipole moment. This dipole moment will be having the direction from negative to positive. From negative to positive, the dipole moment will be there. And we will give this equation as, for electric dipole moment, P bar is equals to Q into D. As Q is a, we know already Q is a scalar quantity, and here D will be the vector that we have to consider. D is tending from negative to positive, negative to positive, right? Right, this is nothing but called as electric dipole. Now let's discuss more about this electric dipole. Means nothing but, we have already discussed about electric potential and electric field due to the single charge, and system of charges also, yes, we have discussed in the previous lectures. Now we are going to discuss about how this electric dipole will exhibit electric potential as well as electric field, okay, on different points around that system of these two charges are around this dipole. Let's see. Electric potential due to a dipole, right? Now here I am considering first a negative charge minus q, and here I will consider a positive charge plus q, which are separated by a distance d, okay, right? And now let's consider a point or, okay, diagram again I will draw here. Here positive charge, here here negative charge, and here positive charge we will consider. Now the distance between them is small d. Let's consider any point P like this. Arbitrarily we have taken a point P, and this is the center of this dipole. From the assumed point to the center of the dipole, I am considering the distance as r, and here in this situation I am considering r is very greater or very comparatively negligible. D value is comparatively negligible when compared to the r. Like this we will consider. And now we have to find the value of Vp. Vp we have to find here. Right, now let me proceed this line in this manner. Now if you draw a perpendicular, okay, if you have drawn a perpendicular like this, and from here also, from here to there, one perpendicular we have drawn here. Why we have to draw perpendiculars, we will see now, we will come to know. This point I am considering as O, this point as A, and this point as B, and that is obviously it is P, right? Now we know the distance between the point P and also the first charge, negative charge, is AP, right? AP. AP is similar, not equal, similar we have to say, similar to this length OP plus OP dash. I will consider this point as P dash, and this point we'll consider as B dash, or else this one let's take A dash and B dash. AP is similar to the summation of OP plus OA dash. Can we consider like this? AP is similar to OP plus OA dash. Why? Because R value is very much greater than D value. It means when compared to the R, this length is negligible length. Okay, that is the reason we can consider in this manner OP plus OA dash. Okay, right. And next, in the same manner here also, BP is similar to OB dash. Okay, this is a negative sign, it will come, no, here. Okay, BP is similar to same OP, but this time minus OB dash. Why minus? Because from here to here the length is OP, and here from here to here is OB dash. That's why we need to consider in this manner. BP is similar to that particular length. That's the reason. Okay, now fine. OP minus OB dash. Yes, as we know this one clearly. Here OP, what is OP actually? OP is R smaller plus what is OA dash? OA dash. OA dash, here let's draw a diagram. Right. From this triangle we can get in this manner. Here this is a 90 degrees angle, and here to here this length is going to be D by 2, as we know clearly. And here A to O distance is what? D by 2. And this length A to A dash length we want here. And let me consider here the angle is theta. If it is theta, this is also an angle theta, like this. Right, and this, as this angle is theta and this length is D by 2, this one will be D by 2 cos theta, right? It means A dash is equals to D by 2 cos theta. In the same manner, R minus D by 2 cos theta we will get for BP, right? That's it. And now what we have to consider here is simply these two things we are going to consider, and we are going to find the electric potential. See, from this lengths, as we found the lengths in between distances, we can easily find the electric potential V. We know already what is the value of V. What is V? V is equals to 1 by 4 pi epsilon naught charge, whatever the charge is there, Q by distance R, right? In the same manner here, potential for this charge, potential due to this charge and potential due to this charge I am considering as V1 and I am considering here as V2. Then V1 is equals to 1 by 4 pi epsilon naught. And here if you see, this is a negative charge, that's why we will keep a negative sign here, and the charge is minus Q. Actually we kept here minus, that's why no problem, we can take only magnitude Q by what is the distance? AP. AP is the distance. What we got here? Okay, let's keep first AP. Then this is equals to minus 1 by 4 pi epsilon naught. Q is there here, and this Q can be written as R plus D by 2 AP. Okay, Q will be written as Q only. AP can be written as R plus D by 2 cos theta. Right. Okay, next in the same manner V2 is equals to 1 by 4 pi epsilon naught Q by BP will come. This is a positive charge only, no need to keep negative symbol. That's why directly 1 by 4 pi epsilon naught Q by R minus D by 2 cos theta will come. Right. These two are the potentials due to two charges at that particular point P. Now potential at P we want means Vp, that is equals to summation of these two potentials, right? V1 plus V2. Vp is equals to V1 plus V2. Okay, let's do that one here. Vp is equals V1 plus V2. Vp is equals to V2, this value is there, and V1, this value is there. Okay, and now in both the cases 1 by 4 pi epsilon naught. Okay, Q is also constant values, we can take them common outside. And next what we got here, 1 by R minus D by 2 cos theta minus 1 by R plus D by 2 cos theta, right? After that Q by 4 pi epsilon naught, and if you do cross multiplication, R plus D by 2 cos theta minus R plus D by 2 cos theta divided by R square minus D by 2 cos square theta, means 2 square means nothing but 4, D square by 4. That is equals to Q by 4 pi epsilon naught, R and R gets cancelled, theta divided by R square minus D square by 4 cos square theta, that is equals to, and here we have to neglect this second value in the denominator because R is comparatively very high than D, right? When if D value is very less, if you square the value of D, it will become still more negligible. Then we don't need to consider that negligible value, right? We don't need to consider the negligible value. We are not just squaring the small value, we are squaring it and again we are dividing it into 4 parts, means divided by 4 is there. That's a completely negligible value, 0.00 something it will come, then we can take that one as 0. That's why we don't need to consider. That's why d cos theta by r square simply. D cos theta by r square. This is Vp equals Vp. And now Vp is equals to Qd cos theta 1 by 4 pi epsilon naught Qd cos theta divided by r square, that is equals to 1 by 4 pi epsilon naught, already we know that is simply a constant. Okay, Qd while we are discussing about electric dipole, I have given Qd is nothing but called dipole moment P. Kp cos theta by r square is equals Vp. Okay, potential at point P due to these two charges are the dipole is nothing but called as Kp cos theta by r square, where r is the distance between the middle of the dipole, center point of the dipole to the point where we wanted to find the potential due to electric dipole. That's it. Vp equals Kp cos theta by r square. That's it. This is nothing but a simple derivation for this one. And now we are going to discuss about electric dipole, electric field due to dipole. That one we will discuss now. Okay, just now we have discussed the electric potential derivation, right? For example, let's consider a small case which are separated by distance two charges. This is a dipole. Let's consider the point is placed here like this, exactly on this equatorial line or else on axial line. How can we find for axial line and equatorial line potential values? Okay, cases, we can say those things are nothing but cases. See, for axial line means if the dipole is like this, plus and minus, and the distance between them is d. Here I am considering the point P, which is at a distance from the center of the dipole is small r. Okay, and from this charge it will be r minus d by 2, and from here this one will be r plus d by 2, the distance. As these values we know clearly, we can directly substitute in the whatever the equations that we got, or else theta value we can substitute. If you see here carefully, the theta value is 0 degrees here, right? On axial line, the theta value is 0 degrees. How can we say it is 0? Because minus here and plus here, if you consider the point here, this angle is theta. If this point is shifted to down here, then it will be 0 only, no? Theta value is equals to 0 if it is in axial line. If it is on equatorial line, means upward, then it will be perpendicular. Whatever the line which you draw from there to the center of the dipole, it will be a line which is perpendicular to the dipole. Then at that time theta value we can consider as 90 degrees. It means in this situation Vp or else V axial, point P, Vp on axial line is, that is Vp is equals to Kp cos 0 degrees by r square, that is Kp by simply r square, where K equals 1 by 4 pi epsilon naught. Right, this is nothing but called Vp on axial line. If you consider on equatorial line, where the theta value is 90 degrees, Vp on equatorial line is Vp is equals to Kp cos 90 degrees that by r square, that equals 0. Cos 90 is 0. That's why it will be 0. It means potential on the point P which is on equatorial line will be is equals to 0. You can consider here another thing. If you consider here an equipotential surface, equipotential surface like this means, example, let's consider these two are one is negatively charged body or else negative charge and positive charge separated by a small distance small d, and if you consider here a plane, okay, if you consider here a plane exactly crossing the center, then this plane, okay, this plane is an equipotential surface with potential 0, equipotential surface with potential 0. In a clear diagram if you want, let's see here minus charge and here plus charge, and let's consider here a plane like this, and this line is making 90 degrees here with the plane in 3 dimension. Okay, everywhere if you consider, every point will have equal potential and Vp that is equals to 0. Vp is equals to 0. That is an equipotential surface. In the same manner, if you consider anywhere these planes, we will get equipotential surfaces, okay, depending on the phenomena. Okay, exactly at the center it will be 0 potential. Fine. Okay, now let's discuss about electric field due to dipole. Electric potential due to dipole is easy because electric potential is a scalar quantity. Whatever the value comes, we will add them directly. But electric field is a vector quantity. We cannot add them directly. We have to use vector addition. Vector laws are must and should there. That's why a little variation we are going to see while deriving it. Let's see that. Electric field due to dipole means nothing but electric dipole. Next, here I am considering a negative charge and here positive charge separated by a distance small d. Okay, and here arbitrarily taking a point P. First, we can study about axial line, electric field due to these 2 charges on axial line and these 2 charges on equatorial line. After that, we can study this point, or else in this manner also we can study. From this method, with one derivation, we can remember both the cases easily. Right? This is the point P. And now, this angle I am considering as generally theta in like before case. Here we have to find electric field at this point. That's why what I will do, this point I am going to give some displacement. I am going to give some displacement to the point P along radial direction, means along R, as well as perpendicular to this R. Okay, it means up to here I have given some displacement P dash. Okay, and that displacement is small displacement dr, and from here to here P2. Okay, this is P1, this is P2. If you consider here, R value is not changing. Okay, here it is R value, here this is also R only we have to consider, because this is a very small displacement, no, that's why this length and this length both are same only we need to consider. But what changed here? Here the angle changed to d theta. For the displacement from P to P1, distance is changed to dr. For the displacement from P to P2, angle is changing from theta to theta plus d theta. Okay. For P1, R plus dr. For P2, we are able to observe theta plus d theta. It means in first case distance is changing. Okay, theta is constant. Okay, in second case theta is changing, R is constant. Okay, right, these two things we need to remember. Now we will enter into the derivation part. Right, now first we have to find the electric field due to these 2 charges, or else due to this dipole, not separately, we are not separately finding these 2 charges. Okay, we are going to find by using the dipole moment. Just before we have discussed about dipole moment, the potential due to dipole moment, how it will be, we know already. From potential we are going to find the electric field. See, already we know the relation between electric field as well as electric potential. What is the difference? What is the relation? That is, electric field E is equals to dV by R. Okay, and now in this situation, in this present situation, if you see, E1 is equals to dV by, here R value if you consider means for this situation here P dash P dash, this is a general formula, and dV by P dash we have to consider. Okay, no need to consider this one, better. E1 is equals to dV by P dash, that is equals to, what is dV by, okay, here negative sign is compulsory because the relation represents negative sign here. E1 is equals to minus dV by P dash. Okay, let's keep dV like that only. What is P dash? P dash is dr, and I am changing this one as dou V by dou R minus dou V by dou R. Here dou represents that partial differentiation, means here we are going to do differentiation only for R, only the terms which represents R, not theta. Theta is a constant, it means dou represents theta is constant simply. E1 is equals to, right, electric field E1 is equals to minus dou by dou R into V like this we can write. What is V? V is potential due to electric potential due to dipole. Electric potential due to dipole. What is electric potential due to dipole? Just before few minutes we have found, that is 1 by 4 pi epsilon naught Q by Q d cos theta, right? That is P cos theta by R square. P cos theta by R square we know, this is nothing but V value. Let's substitute in this equation, that is minus dou by dou R into of 1 by 4 pi epsilon naught P cos theta by R square. We will keep like this, and next as here minus sign is there, we will shift minus sign inside, and whatever the constant terms are there we will bring them out. That is P cos theta divided by 4 pi epsilon naught, okay, minus sign let's keep outside only, minus, and dou by dou R of 1 by R square. Like this we will consider, this is nothing but E1 value, that is minus P cos theta by 4 pi epsilon naught, and here dou R d by dx of 1 by x square formula we need to use here. That is simply what we will get here, R square is there, if you shift this one to upside then it will become minus 2 R power minus 2 d by dx of x power n into x power n minus 1 formula, just mathematical things we know, right? How we have to do that? Minus 2 into R power minus 2 minus 1, that is minus 3, minus 2 into R power minus 3, that is equals to minus minus will become plus, that's why P cos theta, okay, 2 is there, 2P cos theta by 4 pi epsilon naught into 1 by R cube. That's it. This is the value of E1. Okay, this is E1 value. E1 is equals to 2 Kp cos theta by R cube. This is the first value. This is the first value E1. Electric field due to this displacement. What is the displacement? Here to there, that's it. Just now we have discussed about E1, right? We got E1 is equals to 2 Kp cos theta by R cube. Fine. Now we have to find the value of E2. Let's see. Actually according to the diagram, if you see just before diagram, minus and plus, and this distance is small d, right, and here the point P is there, this distance is r, and the displacement along PP2 is d theta and r, right. This is the actual displacement. This displacement value we need to find, we need to get it, means PP2 is equals to what, we have to get it here in this case. From this diagram, if you see carefully, this is the radius and this is also radius only, and this is like a arc. Length of the arc is r into d theta, that's what we have given here, right. dV by PP2 is equals to dV by r into d theta, and here r into d theta we got, right. Now E2 is equals to minus 1 by r, keeping separately. Next dou V, dou by dou theta of V, we are going to find this equation, that is minus 1 by r into what is V value, d dou by dou theta into 1 by 4 pi epsilon naught. This V value is for the dipole, that is P cos theta by r square, that is minus 1 by r into here P cos theta, P is a constant and this is also a constant term, and here r square is also a constant term, because in this situation only theta is changing, not r is a constant term, that's why we can bring out r, that is P by 4 pi epsilon naught r square, we are taking out, into dou by dou theta of cos theta, or else dou cos theta by dou theta, we will keep like this. This is equals to minus P by 4 pi epsilon naught r cube into dou cos theta by dou theta is minus sin theta. Okay, it will go like this, and we will get E2 is equals to P sin theta, or else Kp sin theta by r cube. Here K is equals 1 by 4 pi epsilon naught. We know the value of E2, and we have found the value of E1 also, that is equals to 2 Kp cos theta by r cube. E1 we know, E2 we know, right. Here from here to here, as the displacement happened, we are going to get E2, and this one dr, here we will get E1. Okay, it means along this line E2, along this line E1, and the resultant of these two is E bar, E2 bar, E1 bar. Now if you do vectorial addition, means E bar is equals to E1 bar plus E2 bar, that is equals to, what is E1 bar here, this one, and E2 bar, just substituting the values, that is equals to 2 Kp cos theta by r cube whole square plus Kp sin theta by r cube whole square whole under root. Okay, this one we need to do. After doing this one, let's see what are the things which we can take common outside. P is common, K is common, and r cube is also common. That's why Kp by r cube we can bring out from the root, and we can keep like this, that is 2 square means 4 cos square theta plus sin square theta. Sin square theta we got. This is E value. E is equals to, that is Kp by r cube under root of 4 cos square theta plus sin square theta. Sin square theta can be written as sin square theta plus cos square theta is equals to 1. Then after doing that calculation, what we will get, 3 cos square theta plus 1 we will get. 3 cos square theta plus 1, right. This is nothing but the electric field value, means magnitude value. You just want this one, you can keep in this manner also, like this. That is E bar or E is equals to Kp by r cube into under root 3 cos square theta plus 1. And here if you want to mention here an angle alpha also, we can mention by using parallelogram law of vectors. You can find tan alpha and all also, right. This is all about electric field due to dipole. Okay, in this also we need to see the special cases. Special cases means simply, let's see now. If theta is equals to 0 degrees and theta is equals to 90 degrees, if theta equals to 0, let's see, substituting theta equals 0 in that equation, cos 0 is 1, that is 3 plus 1, that is 4, that is 2, that is simply E is equals to 2 Kp by r cube will come simply. Next, if theta equal to 0 degrees, this is E is equals to, if theta equals to 90, that is Kp by r cube. If theta equals to 90, that is this value will become 0, under root 1 is 1, that is Kp by r cube. Okay, it means simply we have to say at 0 degrees electric field will be double. Okay, electric field will be double due to dipole when compared to the electric field on the equatorial line. That's it. This is simply nothing but these two special cases. This is if theta equals to 90 degrees. That's it.